Hello students, in the last project we learned about the overall structure of aircraft engines. In this class we will start to learn about the working system of aircraft engines. Have you ever noticed what the engine of the car we take for daily travel is made of? As shown in the figure, in addition to the crank connecting rod mechanism and the valve mechanism, it also includes 5 major systems, namely the fuel supply system, lubrication system, ignition system, cooling system, and starting system. Similarly, in aviation gas turbine engines, in addition to the main components we have learned before, such as the compressor, combustion chamber, turbine, tail nozzle, etc., it also contains many working systems to ensure the normal operation of the engine, such as the fuel control system, lubricating oil system, starting system, etc. First, let us learn about the control system. What is the engine control system? In order to maintain the given working state of the engine, or change the working state, according to the required rules, the engine must be controlled in order for the aircraft to fly at different altitudes and speeds. In the history of the development of aircraft engines, the control system has evolved from the initial piston engine speed automatic regulator that changes the propeller pitch to the gas turbine engine speed, temperature, oil start, acceleration, and other control systems, as well as anti-surge devices, to ensure the safe operation of the engine over temperature and over speed limiters, etc. In addition, as the performance of the engine improves, more and more stringent requirements are put forward for control. More controlled parameters need to be controlled more accurately, and thrust management system, control, fault monitoring, etc. are required, all of which make the engine control system a complex multi-loop control and management system. Due to the expansion of the flight envelope, the characteristics of the engine vary greatly. Within this range, in order to meet the needs of the aircraft under various flight conditions with high performance, there are many controllable variables, and the control system is also very complex. Different types and different uses of engines have different requirements for the control system. Therefore, there are some basic requirements for the control system. First, use the engine most efficiently and maximize its potential under various working states and flight conditions. Second, any control system must be stable, that is, it must be able to maintain a stable working state according to a predetermined rule under the influence of external interference. Third, the dynamic process of the control system should have good quality, that is, good rapidity and appropriate attenuation oscillation characteristics. Fourth, reliability is the basic requirement of the control system. In addition, it is also required to be easy to maintain and adjust, easy to detect faults, short replacement time, and even allow some components to work with faults. Fifth, during the development and testing process, the control program can be changed quickly and easily, and the parameters and system components can be adjusted at any time. The control system can meet the functional requirements of the engine expansion. Sixth, the control system should have a simple structure, light weight, small size, and easy installation. With the development of aviation engine technology, engine control has assumed more and more tasks, including fuel flow control, airflow control, clearance control, cooling control, turboprop, turboshaft, engine control, supersonic aircraft control, etc. Here, we mainly study the fuel control system of the engine. Fuel flow control is to supply clean, vapor-free, pressurized, and metered fuel to the combustion chamber, according to the different states of the engine, including starting acceleration, steady state, deceleration, reverse thrust, etc. The control requires no surge, no overheating, no overspeed, no rich fuel flameout, and no lean fuel flameout. This is also thrust control, transition control, and safety limit. Thrust control is to meter the fuel supplied to the combustion chamber according to the working state of the engine and the flight state of the aircraft to obtain the required thrust. Thrust control includes speed control, pressure ratio control, and reverse thrust control. The purpose of transition control is to make the engine state transition process proceed quickly, stably, and reliably. Generally, it includes the control of the starting acceleration and deceleration process and the anti-surge control of the compressor. The purpose of safety limitation is to ensure the safe and normal operation of the engine and prevent over-temperature, over-pressure, over-speed, and over-power. The safety limitation system will only work when over-temperature, over-pressure, over-speed, and over-power occur. As shown in the figure, when the engine is operating under ground conditions, it is subject to safety restrictions of maximum speed, lean flameout, maximum value of total temperature of gas before the turbine and compressor surge boundary. In the air, at high altitude and low speed, it is limited by flameout of the combustion chamber at high altitude. At low altitude and high speed, it is limited by compressor overpressure. Next, let's look at how the fuel control system works. The fuel control system controls the fuel mass flow according to a predetermined control scheme based on the throttle position, flight conditions, and atmospheric conditions. The engine control scheme refers to changing the controllable variables according to external interference, mainly reflected in changes in flight altitude and speed or driver instructions, to ensure that the engine-controlled parameters remain unchanged or change according to a predetermined rule, thereby achieving the purpose of controlling the engine thrust. Adjusting the fuel mass flow to ensure that speed n equals constant is one of the most commonly used control schemes. The engine control system consists of a control system and a controlled object. The main components of the control system include sensitive components, amplifying components, actuators, fuel supply components, etc. According to the control principle, the engine control system can be divided into closed-loop control systems, open-loop control systems, and compound control systems. The first type is a closed-loop control system. The output of the controlled object of a closed-loop control system is the input of the controller, and the output of the controller, the fuel flow, is the input of the controlled object. The signal transmission path forms a closed loop. Its working principle is when the external conditions change and the air mass flow entering the engine decreases, the fuel supply does not change, so the gas temperature rises, the turbine work increases, the engine speed increases, and the centrifugal force of the centrifugal flyweight of the sensitive element increases. The axial force acting on the oil separation or door is greater than the adjustment spring force, and the oil separation valve moves upward, opening the upper and lower oil circuits, blocked by the two shoulders of the oil separation valve. The upper chamber of the follower, piston, is connected to the high-pressure oil circuit, and the lower chamber is connected to the return oil circuit. The follower piston moves downward, the swash plate angle of the plunger pump becomes smaller, the oil supply decreases, and the speed returns to the given value. Its advantage is that the control is relatively accurate, but the control is not timely and lags. The second type is an open-loop control system. The output of the controlled object of the open-loop control system is the engine speed, and the input of the controller is the interference. The output of the controller is the fuel mass flow, so the relationship between the controller and the engine and the relationship between signal transmission form an open circuit, so it is called an open-loop control system. Its working principle is when the flight altitude increases, the air mass flow entering the engine decreases, and the total pressure also decreases. The controller and the diaphragm box simultaneously sense the change in this interference, so the diaphragm box expands, and the opening of the baffle valve is increased through the lever and the oil discharge of the upper chamber of the follower. Piston increases, so that the follower piston moves up and drives the swash plate angle of the plunger pump to become smaller, and the oil supply decreases to adapt to the decrease in air mass flow, thereby keeping the speed unchanged. This control system has timely control and small lag, but because it cannot sense all the interference, the control is not very accurate. The third type is compound control system. Compound control system is a combination of open loop and closed loop control. This control system has the advantages of both open loop and closed loop control systems, that is, timely and accurate control and stable operation, but the structure of the controller is more complicated. Students, in this class, we learned about the engine ZIO control system. Understanding its three control methods is a difficult point. I hope that students will review and digest and absorb the knowledge in time after class. Thank you.